Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we're going to talk about the statistics that get used in the use of the 7 quality tools. In an earlier video, I showed you roughly how I would use the 7 quality tools, the order that I would use them in order to solve a problem. Now, I didn't talk about statistics that were in those techniques, but I want to show you how the statistics are sort of peppered through the process. Six Sigma has a reputation for teaching people quite heavy mathematical statistics, but I want to show you that it's very rare that I would get heavy statistics out of the box. It's very rare I have to do some fancy calculation. Just occasionally there is a very specific tool that needs to be used, but software is going to help you enormously. So I want to show you the 7 quality tools and some of the implicit statistical techniques that I'm using along the way. But I don't really do any statistical calcs along the way, but I'm standing on nice firm statistical ground because that helps me to make better decisions about my process and my problem. So let's take a look at this. So we've got the 7 quality tools and the stats that's in there. Okay, so in a previous video I kind of showed you the 7 quality tools and the order that I typically use them, and I think I said at the beginning I would typically start off with a Pareto. This would be the one that I would use in order to find the problem in the first place. Then once I've got the problem, I'm typically going to go like this. I'm going to go run chart, histogram, CPK, and I always do those 3 with variable data. So run chart, histogram, CPK. I find out that my process has got too much variability and I need to squeeze this thing in. So we have a problem here. What am I going to do next? Well, I'm going to use the flow diagram. I'm going to use cause and effect diagram, and I'm going to squeeze that in. I'm going to create a control plan, and then finally, once I've got the process under control, I'm going to lock it in with an SPC chart. And that was the description that I used in a previous video, and at no time did I mention any sort of stats or anything like that was in the process. And a lot of times what I'm just doing is using very simple rules, or they're just implicit in the tool. So let me show you. We'll start off with the Pareto and the run chart at the beginning. Now the first thing at this point is going to be sample size. Now you will have been taught how to calculate sample size as part of your Six Sigma green belt or black belt class. Do I calculate sample sizes? Very, very rarely. I use simple rules of thumb. I know that I've got an estimate. So this Pareto is going to give me an estimate. This run chart, histogram, CPK are going to give me estimates. If I want to get good estimates of what's going on, what's one of the things I've got to do? I've got to have a good sample size. Now the Pareto typically is count data. So because it is count data, the rule that we use for count data, the sample size, is between 1,000 to 3,000. So I'm typically going to err on the smaller side of that, and I'm going to look for 1,000 data points, 1,000 errors, 1,000 mistakes in order to get a good signal of what my biggest problem is. Now, how does that normally manifest itself? It normally shows up with a Pareto that has got at least a month's worth of data on it. So I would look at my Paretos monthly, no shorter than that. because I won't get the right sample size on there. So having got enough data, now I can pick the right problem. Now I can get on with problem solving. Now, run chart. Now specifically, if I'm going to do a run chart, histogram CPK, variable data. Again, there's a sample size needed here, and if it's variable data, the rule is 30 to 50, 1000 to 3000 if you're counting something, 30 to 50 if you're measuring something. Am I doing a calculation? No, I don't do sample size calculations. I use a simple rule of thumb. Okay, what else is going on here? Now then, when I look at the histogram, what's one of the things I'm looking for? I'm looking for the data to be normal. Why am I looking for the data to be normal? Well, because the CPK diagram relies on the normal distribution to make a calculation of the defect rate. It calculates the tails. So these calcs in the CPK diagram are estimates, and they're estimates of the long-term defect rate. So what's one of the things I want to know by looking at the histogram? Well, I want to know that the underlying data is sort of following that pattern. So I'm looking on the histogram for it to be following something that approximates to a normal distribution, so that when I use the CPK diagram and it calculates, it estimates the long-term defect rate, that the estimate is a good, accurate representation. Now then, how does it do that? Well, it uses a probability calculation. Now you might have been shown how to do probability calcs in your Six Sigma training. Certainly in my green belt training I teach this. Do I do a probability calculation at this point? No, it's part of the CPK tool. So when I ask the tool to do the diagram, when I ask it to do the calc for me, I'm leaning on a probability calculation. In order to make sure that the probability calculation is true, I look for normality. Now, by the way, I just look for it. I'm not going to do any test for it. There's no hypothesis test to do this. You can do it, but there's no need to do it. Look, it's an estimate. Does the shape go up in the middle and down at the ends? If the answer is yes, the estimate is going to be useful to you. But you've got to bear in mind, the number that it's calculating here is an estimate. So if you take a look at this CPK diagram here that we've looked at previously in a previous video, you can see, look, defects per million, 44,052. Yeah, there is the estimated defect rate. It's not an observed defect rate. That is a probability calculation. I'm not doing any probability calculations though. I just know it's there, and therefore I have to check for normality. Okay, what else is going on? Well, okay, once we get the problem now and we're trying to squeeze this thing in, there's other statistical tools that I might draw on. So I've just drawn the 7 quality tools here, but once I get to this point, one of the tools that I might draw on here is measurement system analysis. In other words, how good an estimate does my measurement system give me? Don't forget, every number you look at is an estimate, and then the statistical tools are helping you to get good estimates, because then you can make good decisions. Good sample size here, good estimate of your biggest problem. Good sample size here, good estimate of your defect rate. Normality here, good estimate of your defect rate. Obviously you've got this data set. Is it a good estimate of what's going on? Do an MSA. Now again, do I do any calcs? Well, not really. The computer does the work for me. But I know I need to find out what sort of estimate have I got coming from my data sets. So there's an additional statistical tool there, and of course it's an additional tool to the 7 quality tools, getting a little bit more mathematical there. Then when we get into SPC, now again, the software is going to do the calc here, but I understand the basics of SPC. A process is said to be under control when it is stable and predictable. What does that mean? Well, stable means that the signal doesn't move. Okay, so when you've got a data set, there's the signal, which is the middle, and there is the noise, which is the spread, the range of the data. When a process is stable, the signal doesn't move. In other words, the average, the mean, stays where it's put. Okay, so if we look at this data set that we looked at earlier, we looked at the run chart. I look at the run chart to assess that the process is nice and stable. You can see that on this run chart here that we looked at earlier. The other thing I'm looking for, of course, is that the noise doesn't move. Now, the noise really is the range. Of course, the way that we assess that is often via standard deviation. So standard deviation and range are both measures of noise. Because if we do an SPC chart, we are often doing an X bar R chart. This is stable. The X bar is checking that the mean doesn't move. The range chart is checking that the noise doesn't move. Stable and predictable. Now again, I'm standing on statistics. Am I really sort of understanding every statistical calculation, etc.? No, the computer is doing the work for me. But I know how these things work, and that's how I use the statistics. Not that I can sit down with a calculator and a pen and do the calcs manually. Now what I'm doing is I'm using them to make sure that constantly I've got good estimates of what's going on. By the way, the X bar R chart is an estimate. What's it? Another word for it? It's an estimate of your process behavior. And it's telling you whether there's something important happening to your process, but it's an estimate of what's going on. So the statistics constantly are helping me to tell that my estimates are good. The MSA tells me that my measurement system's good. The histogram tells me that the estimate of the defect rate's going to work. The CPK diagram is a calculation. We need to make sure that the calc in here, is it a good estimate? Sample size, is it a good estimate? Everything is helping me to make sure I make fantastic decisions, but I'm really just leaning on the statistics. I'm not doing the statistics and doing lots of mathematics. But if I understand the underlying principles and I use them, I will make much better decisions. I will learn how to get my process to behave itself. I will learn how to get my CPK inside those tolerances, and of course ultimately I'm going to make pots and pots of money. The 7 quality tools with statistics built in.